Ну вот, говорю, говорю. Пришло что-то, да? Все нормально, да? А, Дима заболел. Не... Просить кого-то, чтобы он прислал. 1, 2, 3. И раз, два, три. 122.
Значит, мне пришлось уже дважды, значит, надо увеличить объем почтовых ящиков, приходите, говорите.
Алло.
Здравствуйте.
Здравствуйте.
У нас программа немного изменилась, потому что первый выступающий сегодня отсутствует, он приболел, вот. Поэтому мы
Угу.
начнем немножко с задержкой.
А, с задержкой. Хорошо, то есть я жду, да?
Да, да, да.
А до скольки мне ждать до моего времени доклада, да?
Да, да.
Угу. А на языке каком доклад? На английском?
Да, на английском, но
Все.
когда chairman подойдет, можно будет обсудить, он скажет, как будет сессия проходить.
А, chairman скажет. Хорошо, то есть начинается в 10:20, правильно?
Да, да.
Угу. Хорошо, спасибо. Все, тогда
Мгм.
я на связи, но пока отключусь. Угу.
Окей. Да, Аля. Доброе утро. Я вижу, что у нас... Больной на голову немножко. Я вижу, что у нас отсутствуют иностранные участники. Есть предложение доклада делать на русском. Какие будут соображения?
Ну, я не против. Доброе утро.
Да, ну хорошо, давайте продолжим. Так, у нас первый доклад, он онлайн. Название здесь присутствует. Так что let's start our session. Good morning, dear colleagues. Okay, let's start.
Доброе утро, дорогие коллеги. Во-первых, я приношу свои извинения за то, что я не могу очно участвовать на этой замечательной конференции, поскольку вот она запараллелилась, к сожалению, с другой конференцией. Я вынуждена делать доклад из Воронежа, из Воронежского университета. Но вместе с тем большое спасибо организаторам за то, что вы пригласили меня сделать этот доклад, и я надеюсь, что он будет интересный и для конференции замечательной Advanced Laser Technologies. Ну, вначале я хочу кратко представить свою научную группу. Это группа молодых ученых. Мы называемся лабораторией физических методов биосенсорики и нанотерагностики, и находимся мы на кафедре медицинской физики на физическом факультете МГУ. И основные исследовательские интересы нашей лаборатории связаны как разработкой различных наночастиц, которые являются наноконтейнерами для доставки лекарств, и которые мы можем использовать, ну, пытаемся использовать, изучаем это для...
Прошу прощения, let's start in English, please.
In English. Okay. So, sorry. The main research areas of my lab is development of porous silicon nanocontainers, which we can use for anti-cancer therapy and diagnostics, for theranostics, and also we can development of different effective antibacterial and antiviral agents based on silicon nanoparticles and different composite nanostructures. And also we try to develop of porous silicon-based biosensors for qualitative and quantitative rapid detection of different microorganisms, different bio-objects and molecules. Today I'm going to talk about work that corresponds to the third area of research. And in the present time, we feel so that different infection can spread very rapid, and of course we need to find also rapid method to diagnostic of such infection. And in this regard, surface-enhanced Raman scattering is becoming the most popular method for diagnostic of different biomolecules and also viruses and also different bacteria. And in the right figure, you can see the number of articles that contains the abbreviation SERS, which means surface-enhanced Raman scattering. And you can see that the number grows every year and has already reached 5,000 in the past year. And the diagram below shows that the most articles use SERS in biochemistry, genetics, and molecular biology. And of course, many of us are familiar with surface-enhanced Raman scattering, but science maybe also students in the audience, and I will start brief with the beginning with Raman scattering. So the phenomenon of Raman scattering is based on the effect of inelastic scattering of optical radiation on the molecules of matter, and in ordinary or relays or elastic scattering, light after interaction with the substrate has the same energy. So the same wavelengths and same frequency. But with an elastic scattering, as a result of interaction of light with molecules of matter, the frequency of radiation change. And this is important, very important, that the change in frequency of scattering current corresponds to the vibrational frequencies of the molecules in the sample under study. So the Raman can be used for examination of molecular composition of the sample. And so the Raman spectroscopy can be used for very, very accurately characterization for biological and also, of course, solid state samples for its diagnostic, which used now also in medicine. So what about surface enhanced Raman scattering? So surface enhanced Raman scattering means enhanced Raman scattering of molecules which absorbed on nanoparticles of noble metal nanoparticles or on some nano surface. And two mechanisms which describe this effect: electromagnetic theory, which proposed the excitation of localized surface plasmons, and also chemical theory, which proposed the formation of charge transfer complex between the metal surface and the adsorbed molecules. So Raman signal amplification can reach million times, which lead to low detection limit of molecules which we can find, which we need to find. And of course it leads to molecular specificity and ability to quantify different molecules in complex matrix, and it leads for short detection time and allows the express analysis, and also non-invasive and label-free analysis, and in the most case, very easy sample preparation for this study. So let me move to original research result, what we do in our lab. So we produced SERS active composite substrates, and usually such substrates are based on porous silicon nanostructure. So why we start to use silicon and porous silicon? Because this material is very easy to fabricate and have to enable, say, surface morphology parameters. And we propose several methods to very easy decoration of such substrates with noble metal nanoparticles. And porous structure of these materials lead to very large specific surface area. And we know the different way to functionalization of silicon surface to provide specific sorption of the molecules which we need to analyze. In this report, I show you our recent results, and I start with silicon nanowires. So it is very well-known method of metal-assisted chemical etching of crystalline silicon, which we can use to produce arrays of silicon nanowires. This is a schematic representation of such method. And for the first time in our study, we proposed method of the decoration of such substrate with different metals. So we use silver and gold, and we propose very easy way to decoration of such noble, to how to cover the top of this nanowires with such noble metal nanoparticles. So we just use silver nitrate or gold halide and mix it with hydrofluoric acid. And as results, gold or silver recovered from this the metal sole on the top of nanowires, and it's lead to, and so we can obtain such beautiful substrates which show very, very strong surface enhanced Raman scattering properties. So in this picture you can see a scanning electron microscopy view of such substrates. So you can see here silicon nanowires, and the top of nanowires covered in this case with gold nanoparticles, in this case with silver nanoparticles, and in this two cases with bimetallic silver and gold nanoparticles. Here we use another method for production of silicon nanowires. So in this case, silicon nanowires were obtained by electron beam lithography method, and also surface of such nanowires was decorated with gold nanoparticles in this case to give them their active properties. And the same procedure of the decoration of nanowires we use here, so very similar that we use in previous study. Let's consider how the substrates presented can be used for diagnostic of different biomolecules. First, consider piaceanin. Piaceanin is one of the many toxic compounds produced and secreted by the gram-negative bacteria, which called Pseudomonas aeruginosa. So such bacteria have very bad properties, unfortunately for our health. So it is multi-drug resistant gram-negative bacteria, and it has properties that such bacteria have properties of antibiotic resistance, and it associated with some serious illness like hospital infections such as ventilator-associated pneumonia and various sepsis syndromes. So, of course, the quick diagnostics of this bacteria in clinic is very necessary. And schematic of the piaceanin molecule is shown in the center of this slide, and its Raman modes are indicated here. We use our substrate of silicon nanowires for the diagnostic of piaceanin. And the figure in the left shows the spectra of piaceanin which adsorbed at the very, very weak concentration, 50 micromoles, and it's was adsorbed from artificial sputum for difficult matrix. And you can see that we can recognize the specific Raman, we can recognize this molecule because this molecule have their own specific Raman bands, and we can recognize such Raman scattering in our sputum, which we can use in our study. It was nothing that these spectra were obtained, but these all spectra were obtained by averaging over 2,000 measurements. So we measure very large maps on our substrate, and then signal was average. And moreover, you can see here that we have a very nice point-to-point and scan-to-scan reproducibility. So our signal from Piazzanin was very stable. And then we choose only one of these substrates. So we choose silicon nanowires decorated with silver and gold, with bimetal silver and gold. And we showed that such substrate allow for the detection of piazzanin in artificial sputum down to very weak concentration, near 6 micromolar concentration, and this concentration is required. So we have shown that we obtained required sensitivity of signal detection for clinical application. So it's a very promising result, of course. And in the following study, we try to diagnose bilirubin. So bilirubin is a product of hemoglobin breakdown, and its increasing level in the blood may indicate the liver disorders and lead to jaundice. And jaundice is the most dangerous in newborn when unconjugated bilirubin molecules can quickly rise the toxic levels and causing neurological disease and even death. And of course, also the development very fast and accurate sensitive sensor for bilirubin detection will help reduce diagnostic time and ensure successful treatment of such disease. And in this study, we use substrates of silicon nanowires which was decorated with gold nanoparticles. So you can see scanning electron microscopy of such substrates here. Since bilirubin is negatively charged molecule, for its better absorption, the charge of the surface of nanowires was changed to positive by selenization of such substrates. So the method of selenization you can see here. As a result, the nanowire surface was modified with amino groups. You can see here in infrared spectra. And in the same time, measurement contact angle showed that the surface of the substrates was hydrophobicide, which also good for us because bilirubin molecule is also a hydrophobic molecule. So here you can see a view of the bilirubin molecule and its typical Raman modes. And on the right, Raman spectra of bilirubin powder, you can see it here, and average their spectra of various concentration of bilirubin are presented. And the gray arrow bar, you can see it here, in the average spectra shows the standard deviations, which was calculated from about 3,000 spectra. So as you can see, we can show that we can achieve very weak concentration of bilirubin. We can recognize very weak concentration of bilirubin adsorbed of our substrates, and also we have nice homogeneously of the signal. And also we use artificial urine as complex matrix, and also very nice signal reproducibility in point-to-point and scan-to-scan measurements we achieved. And in the figure of the right shows average spectra of bilirubin molecules, which very, very also low concentration. And for different storage time, from even 7 days of incubation after adsorption of bilirubin molecules. And also the theoretical full wave electromagnetic simulation of Raman scattering presented in the center of the slide. And you can see here that the major contribution to the total search signal comes from the analyte molecules, which located on silicon nanowires near the gold nanoparticles. Therefore, such good reproducibility and signal stability propose that we also can use such substrates in clinical application. And let me move to another study. Here we try to use our gold decorating silicon nanowires, which was produced by dry reactive ion etching for the detection of molecular composition of cancer cells. And in this study, we use breast cancer cells, which were incubated on our substrates for 24 hours and then fixed. And here you can see the scanning electron spectroscopy images of the obtained cells. And you can see that such silicon nanowires covered with gold nanoparticles penetrate through cell membrane. And what is surprise, so you can see it also from the live images, that we did not recognize cell deaths or cell damage during the incubation of such substrate for at least 3 days of incubation. So no die, no dice. And the cells really feel good, feel nice on this substrate, so they even multiply during the incubation of our nanowires. You can see it here in this movie. So 1 cells, and after 2 days on incubation, so we have 2 cells. So it's very nice. So cells really feel very good. And here you can see the search spectra of such cells. And according to the data obtained, there is significant enhancement of Raman signal from cell composition. So we can recognize signal from cell DNA, from inner from mitochondria and different proteins of the cell. And at the left you can see the obtained map. And so you can see that very strong signal from cell observed on the top of nanowires, while completely absence of signal was between the nanowires. So nanowires is very, very self-active, have very, very self-active properties. So such substrates will help us to understand of bioprocess inside the cell. So now we continue our experiments and try to find very interesting results. So in conclusion, I just can repeat that we think that such composite substrates based on silicon nanowires or silicon or porosilicon with noble metal nanoparticles are indeed a very promising material for the creating of very sensitive sensors for diagnostics of various biomolecules. And thank you for your attention.
Thank you for your presentation. Okay, it's quite interesting, of course. So we have some time to discuss. Do you have a question, please?
Okay, thank you. It seems that your substrates they should be quite expensive because they're unique. So my question, is it possible to clean it somehow, to use it many times?
Yes, yes. So we use such nanowires. Such nanowires is the most expensive material because in this case we use a very difficult method of ion etching. And we try to use such nanowires several times, and so for at least three times we can use it, and the signal didn't change dramatically. So it's very nice. And what about such material, such nanowires? So such nanowires not very expensive. So because we use just chloride or nitrate of so the metal salt and very weak concentration of such salt, and we can produce the sample with very big area, so 4-inch silicon substrate we can cover it at first with silicon nanowires, then cover it with gold. And in these experiments we crash such substrate for a chip, and chip had size so near half of millimeter, so it's not very expensive substrate.
I have another question. Is it possible to measure something in vivo? I mean that you can use not wires rather than nanoparticles, put it in blood, and measure some chemicals with the Raman spectroscopy just in vivo?
Yes. Yes, I think this is of course not impossible, and sometimes we try to do this, but I also read such paper where not we of course, but some research groups try to use self-active substrates to recognize different process in blood, and also recognize presence of antibiotic in blood, and the study was successful. We also try to do it.
Thank you. Next question.
Yeah, thank you for your talk. Do you consider to use your particles for tip-enhanced Raman spectroscopy? I mean, you can decorate, for example, a silicon tip, silicon cantilever with your particles and obtain...
Yes, I also think that this is what such nanowires is very promising material for tip enhanced, because we can use only one nanowires in this case, yes, and easy and more easy to penetrate inside cells, but we have no such collaboration, unfortunately. Maybe when we find it, so we try to use it.
Okay, thank you.
Any questions? Okay. That's please.
There are many other schemes for cancer, so diagnostics exists in medicine. Can you outline the main advantage of your proposal if compared with other medical techniques?
Yes. Because of SARS effect, we can recognize the very weak changes in molecular composition of cells, which we cannot recognize with other methods. And this method is very fast, so very fast measurements in compare with the other methods. So this is what we can propose.
Okay. Is it okay? Do you have any questions? No. I have some short questions. How do you estimate the number of molecules inside the porous? By using the amplitude of Raman line or something else?
No, we just dilute our suspension to achieve the different concentration. And of course, when we use in clinic application, we can just recognize the presence, only the presence of one or another molecule in different complicated matrix.
Okay, thank you.
So,
Thank you. Okay, any questions? Nothing? Okay, let's Palach.
Thank you. Yes, thank you very much for questions and time.
Really active technique to help us. We have some times before next presentation. Dr. Ochkin. Something. Lagunov. Okay. So we may start. Don't hurry. Let's something explain before your presentation, maybe some words. Okay, let's start. We have 5 minutes. Можно здесь?
Good morning, dear colleagues. I'm here today on behalf of the low temperature plasma spectroscopy department of Lebedev Physical Institute of Russian Academy of Sciences. And today I would like to talk about the determination of particle concentrations from absorption spectra obtained with fast frequency tuning. Firstly, let's recall the methodology behind the absorption spectroscopy. Basically, what happens is the probing light goes through the media and gets detected after passing through it, and by analyzing the features in the transmitted signal, one can deduce the concentrations and the temperatures of the absorbing species. Today we are going to talk about the special class of methods which requires frequency tuning. And what's more, we are going to divide this class of methods into two, which of those are single pass methods and multi-pass methods. Multi-pass methods differ from the single pass methods in using optical cavities to increase the optical path length in the media in order to increase the sensitivity. So a few words about the effects of fast frequency tuning on the absorption line form and about the distortion. The distortion of spectral lines is known phenomena. In physics, it was firstly discovered around the 1940s in the nuclear magnetic resonance studies. In optics, they were deeply studied on the example of single pass measurements of different gases with frequency tuning. The frequency tuning rate was in the order of 10 to the power of 6 or even to the power of 7 inverse centimeters per second. The distortions of typical distortions of line profiles can be seen on the picture, on the part B to be exact. The physical reason behind this phenomena is that the incident radiation induces polarization states in the media. These polarization states radiatively relaxate and interfere with the primary radiation which causes the interference, and these structures, oscillatory structure in the absorption signal, can be observed. In 1988, in the Physical Institute, the model based on Maxwell-Bloch equations was proposed, and this model correlated well with the form of the experimentally obtained results. But the question of determining of the concentrations of the species from the distorted lines wasn't fully studied. Let's recall some essential relations for quantitative absorption spectroscopy. Basically, the main purpose of quantitative absorption spectroscopy is the quantitative analysis of gaseous species, plasmas, etc. And the main relation for this is so-called Bouguer-Lambert law for the intensity of radiation that passed through the absorbing species. We can see from this relation that incident radiation exponentially decreases passing through the absorbing species. And under the exponent is the parameter which correlates to the concentration, so-called absorption coefficient. And the second important relation is so-called Kravitz integral, which relates concentration, or in more common sense, the difference between the population of upper and lower states of absorbing species. It correlates it with the integral of the absorbing line in the frequency domain. So in order to find the concentration of absorbing species, we need to find the differential signal of incident and transmitted radiation through the media, and then integrate it and calculate the concentration. But for these relations to work, it's assumed that the frequency dependence of the absorption doesn't change throughout the measurement. And with fast frequency tuning, this situation, this requirement can be violated, and which can cause the problems with determining the concentrations from the distorted profiles. And let's discuss one more question. Why, on the first place, do we might want to increase the frequency tuning rate? In high sensitivity spectroscopy, one of the most important parameters is the averaging time, which is closely, for a set of spectra obtained in one measurement, which is closely related to the frequency tuning rate of the laser. The faster the laser is tuned, the more spectra we can obtain in a fixed period of time. to give an example, to achieve an efficient signal-to-noise ratio in our method, so-called off-axis integrated cavity output spectroscopy, with measured differential signal around 10 to the power of -3, the averaging by 10 to the power of 3 to the power of 4 spectra is needed, which corresponds to tuning rate around 10 to the power of 3 inverse centimeters per second, with 1 to 2 inverse centimeters tuning range and 1 second time resolution. But if we want to increase some of the parameters, for example, frequency tuning range, or to get better signal-to-noise ratio, we will need to tune our laser faster to get more spectra in one fixed period of time, which can again lead to line profile distortion and can make estimation of the concentration from the distorted line profiles much more difficult for us. And it's very important to note that in works on single pass methods with fast frequency tuning, less to no attention is paid to the question of determining the concentrations. And one of the few works that takes this question into the consideration is the work of Van Helden research group. It was published in Applied Physics Letters in 2008. The experiment involved quantum cascade laser. It was tuned with a rate in order of 10 to the power of 6 inverse centimeters per second. The absorbing species was methane, to be exact 130 milliliters of methane, and to that concentration, to that pressure of methane was added buffer gas, argon, which caused the line broadening, and it can be seen on the figure 1 that with the increase of the buffer gas pressure, the oscillatory structure on the left gets less and less until it becomes negligible, which can be explained by the collisional quenching of induced polarization states in the media. So to address the number density in this work, Van Helden research group did the following. They used the void profile fit to their data without taking into account, so they took their raw signal and least square fitted this with a void profile, and it can be seen that with big buffer gas pressure it fits pretty well, but with the small but with non-buffer gas added to the mixture and with narrow line of the absorbing methane, the void fit doesn't describe the experimental data very well, which translated to the finesse of the absorbing species concentration determination. It can be seen that in the region of low buffer pressures, there is quite a big error. So on our behalf, we tried the same method with the void fit and obtained very close results, but we also tried some different methods, including integration of absolute values of the spectra, the distorted spectra, integration including the negative values, and integration neglecting the negative values by zeroing in. And we can see that the error gets smaller and bigger with different mathematical methods, but all of these methods are not quite physically descriptive. So we decided to dig a little bit deeper. There is one, not even one, but a few more sides to this issue. First of them is that due to peculiarities of quantum cascade lasers, with the increase of the tuning rate, the bandwidth of the system decreases, so it becomes necessary to take into account instrumental function. This is exactly what we did. We took the data for the bandwidth from the article and convoluted a set of different void lines for different concentrations. And we were looking to minimize the residual signal on the right wing of the experimental profiles, which are points on these pictures. And we can do this because of physical reasons, because when we scan the frequency from the higher to the lower wave numbers, the right wing of the line contains true information about the concentrations, because the induced polarization states didn't become to relaxate and don't interfere with the incident radiation. And by minimizing the residual on the wing, we recalculated all of the spectra and obtained values which correlated with the known ones much better. And one more thing that's important to note is that instrumental influence on the area of profile is negligible, because we use the convolution with the Gaussian function with the unit area, and as you can see, the concentration computed from the integration of the line convoluted with Gaussian profile with different bandwidth stays the same. So bandwidth can be used as one of the fitting parameters freely. And now a few words about our research. It's not single pass, it's multi-pass. It uses the high-Fanese cavity made of mirrors 1 and 2 and special alignment of beams inside the cavity, which ensures that they are not interfere with each other. And one more important thing, that in such systems the optical path length inside the cavity is such big that it can be that all the calculations and all the phenomena in this cavity can be studied in the intensity domain, because lasers coherence length is much shorter than the optical path length inside the cavity. So using this multipass cavity, we performed a few experiments with on different wave numbers with different molecules, oxygen, including oxygen and water, and obtained a few spectra with different frequency tuning rates. It can be seen that with increasing of the frequency tuning rate, the lines became more and more distorted. These phenomena cannot be explained with coherent wave interaction like the first one, but we have the explanation too. So the point of this phenomena is that the multipass cavity has so-called ring down time, rise and fall time for the light that goes into the cavity. And if this ring down time is compatible with the time that's needed to scan through the absorption line, the lines become the distortions of the line profiles become obvious. Also, we have proposed finite difference model and published it, which corresponds to the experimental data really well. And we performed the calculations using the differential equation for the intensity on the outside of the cavity, which can be seen on the picture in lines, and points the experimental data. And we performed, we determined the concentrations from the integrated absorption lines, and it can be seen that in experimental and calculated values for the determined concentrations from the distorted line profiles are not so dependent of the tuning speed in that case. And to the conclusions. We have studied the possibility of determining the concentrations of the absorbent species with fast frequency tuning around 10 to the power 6 and inverse centimeters per second, and proposed a method to obtain the true concentrations from the distorted profiles, and developed special software to do this reliably. And using the examples of water and oxygen, we have studied the phenomena in the multipass cells with much lower tuning rates, and came to the result that such distortion mechanism allows to use classical relations between particle concentrations and integrated absorption. Thank you for your attention.
Thank you. Do you have some question, my colleagues? No questions. Okay, I have some short questions. You remember about measuring water molecules by using this technique? My question is, could you separate the water molecules from ortho isomers to para isomers? Do you know that the water molecule has two isomers? One of them is magnetics, has a magnetic moment, and another one no magnetic moment. Do you have separated this in your experiment?
But do they have the similar wave numbers? Do their transition have the similar wave numbers?
No, it's separate. Of course, that's every molecule has a different absorption line, of course.
We used the plain water absorption.
Okay, thank
lines.
you. Any questions? No questions. Okay, thank you.
Thank you very much.
Again. Dear colleagues, we have some time. I think we can take the coffee or tea, if it's possible, I don't know, for the next presentation. Dr. Lednyov? 11:14. А где куница? Окей. Ну, давайте. So, okay, we have next presentation. Let's wait a little bit, and we may. So it's Ponurovsky, from Ponurovsky? Okay. Hop. You know, broken the legs. Okay. So, no. Let's start in English. Okay. no, if you have some problems, you may make it. Don't hurry, don't worry, no problems. Let's start.
The presentation is prepared by Kunitsina Ekaterina, but she's broken his leg and asked me tomorrow morning to give some information about our work about using the high-speed photodetectors for precision diode laser spectroscopy. This work is have done with some groups from St. Petersburg and from diode laser department of Academy of Science by in Moscow. The next, please. Our colleagues from St. Petersburg give us some photodetectors for testing and use in our applications for different in different types of techniques. This is some photo and types of the semiconductors, and here are absorption bands which we use classically in our devices. You see this is some gases on the right of this picture, this ammiac, methane, and these molecules we are using with diode lasers and photodetectors. Blue markers are which photodetectors we have in our laboratory. Here are the spectral response of classical photodetector which we use in our application, because we use classically this region. And next, it's the parameter of photodetectors. The main thing for us is the sensitivity in this region, because the most of our measuring molecules are in this region. This is some photo from Ekaterina to show how it's look like. And this is some slides about our department diode laser spectroscopy. Now we test some screening device to measure these purities with some limits. Now we are testing this device with our colleagues in Moscow Clinical Hospital, and we have some publications I can send you if it need. And also we use the detectors in our work with Nizhny Novgorod to control impurities in the process of high purity hydrides. This is multipass cell, and this is the signal of the photodetectors with the diode laser which we use for measure. I think this is ammiac. And also some years ago we have a system to registration measure house gas of more than a high. This is some parameters of this system. And in conclusion, and also must measure that we use the photodetectors and our diode lasers with patients group to measure some purities in Vaksansk observatory, the same method. I think, sorry for my presentation, this all, I take maybe some thoughts add to my words.
Thank you for your first presentation. I believe it's a record. Let's discuss a little bit. Do you have some question? No. Okay. Let's.
Can you make some comparison with other detectors, say germanium-based detector for this spectral region? You are talking about some special design, but is it better than known or not?
I think it's not very better, but 10 years ago we used Hamamatsu detectors, but now Hamamatsu and Germanium. Yeah, it's a Germanium, but now it's not available for us about 3 years, and we use this one. That's why. I asked to Katerina and can send you because I have seen some articles of their group with other photo detectors. Yes. No.
Okay, thank you. Any questions? No. Okay, thank you for your presentation that you have mentioned about our mutual experiment in Caucasus inside the tunnel Baksan Neutron Observatory. I need to show this channel in my presentation for 1.5 hour later. Let's thank you for this group because we use its technology to measurement of magmatic CO2 gas for 12 and 13 because it's marker of the volcanic activity. It's very important for us and it's very successful experimental data. Now we have analyzed it and we are going to continue our collaboration and now we're working on the prepare special laser analyzer for analyze the volcanic gases inside this tunnel, and we have produced, we have development such as very compact and very stable laser analyzer based on this technology. Okay, thank you. Let's analyze again. So I think we have some minutes to make coffee break. I don't know it's allowed us or not. Let's start and check it. Next presentation is Lidnyov. So let's come back 11:14. We have 15 minutes.
Еще минута. Минута еще.
Все, поехали?
Минута.
Не понял.
Минута еще.
Еще минута? Ну,
да, а нам сказали только на английском. Yes, we were told by the chair that we should use English only. I don't know. Officially, the official language is English. Okay.
Докладчик на месте, презентация на месте. Let's start. А, у нас как там? Следующий, там есть тоже окошко, да? А, он будет, да? А, хорошо, а после меня? Все на месте. Окей. Ну тогда что, раз у нас следующий докладчик на очереди, начинаем. Let's start, dear colleagues.
Okay, thank you. My name is Vasily Lednev, and I'm at Prokhorov General Physics Institute, and we are developing devices called LiDAR. These are devices that can measure something remotely, and for some application that can be crucial and very, very important. So we trying to develop compact LiDAR system. They should be small, and they should be, we try to, that they should be eye safety. So just brief description what the LiDAR is. That is come from this abbreviation, but the instrument is very, very simple. So if you have a pulse laser that generates a laser pulse, you direct it to a remote target, then this pumping scattered at the target. It can be elastically or inelastically scattered. You collect the photons, measure the spectrum with the gated detector. So if you know the delay between output laser pulse and the photons you catch, then you know the distance to the target. And if you interpret the spectra, you know something about your target or object you're interested in. Okay, from the power density, I will discuss these 4 lines that will be for elastic scattering LiDAR. It can be fluorescence or Raman LiDAR. That also can be, you can induce a plasma if your power density high enough. Nowadays, filaments are also used for LiDARs, but this technique extremely expensive, and so I just show only these 4 results. So why we need LiDAR? This is a good example of unique scientific experiment that is held by NASA at Mars surface. Here is a rover. It's called Perseverance rover. It holds different equipment, including a SuperCam instrument. This instrument combines elemental analysis, molecular or phase analysis with the Raman spectroscopy, and laser-induced fluorescence instrument that can provide you some more information about rocks, about soils, and the primary goal of this instrument is to find out any traces of life in or maybe past life. Quite nearly the same mission will be held by ESA, but now it's delayed due to problems with the rocket. Okay, and now I give you results why it is important to use laser-induced breakdown spectroscopy and Raman together. Because if your sample like carbon calcite, it have different polymorphic modifications. With elemental spectra you have the same spectra, but with the Raman you have different, so you can differentiate. It's quite important for geologists to distinguish the condition where the rocks are formed. Alternatively, if you use Raman spectroscopy for real samples with a mixture of different crystals, it sometimes became very difficult to distinguish these lines and to carefully interpret the Raman spectra. So LIPS technology can give you some ideas about elements of your sample, and that helps you much to interpret the Raman spectrum. Okay, so Raman gives you molecular analysis, while LIPS give an elemental. So if you combine, you get much more interesting result than separately. And we decided how to do it with a single instrument, with a single LiDAR. And the idea is basically shown here. So if you have two laser pulses with a delay between them, then you can measure a Raman spectra with the first one. I draw it with low energy to prevent damage. And then you can evaporate, damage your sample, and measure the LIPS spectrum. And that can be done during the single laser run. So we did it in our lab, and just example of spectra of gypsum and anhydride samples. These are the raw Raman spectra. You see they're quite noisy because this is remote sensing. And the same for LIPS spectra. So that's work fine, but you can go further. For example, if your target is covered with a dust or covered with something, you can clean it with the LIPS spectrum. So here is an example of Raman spectra of marble, and marble coated with gypsum dust. So if you measure the Raman here, you can see only gypsum. You can say nothing what is beneath this dust, but with the LIPS you can do it. So you just blow off the material and see what's happened. This is for remote biologist measurements, but if we talk about military application and safety, you can do the same with the explosive material stored in bags. For example, these are ammonium nitrate that was stored in a black, thick polyethylene bag. And with such system, when we make a hole and then measure something from very, very small hole, we can see the Raman spectrum. So this is the raw material, and the blue one is through the hole. And when we play with this, we found out something interesting. When we analyze Raman spectra of highly turbid materials like powders, it's quite difficult to measure the Raman spectra because efficiency of Raman scattering is quite low compared to the elastic scattering. And we observed that if we make a small hole by a laser, so-called laser crater, the Raman spectra increase very much. It's about 15 times it increase when we use such hole. We call this technique laser crater enhanced Raman spectroscopy. It's a good way to enhance the Raman spectra of powder materials remotely, the only one we know at the time. So we try, here's the laser crater profile, that is the sampling beam. So if we move the sample and measure the enhancement factor, so it drops very rapidly, so it works with the crater. The same is if we change lens to sample distance. So the maximum effect is about 14-fold. This is the two-dimensional image of sampling spot. Here is the scheme. That is a projection of the target surface to the spectrometer. So the laser pot is always smaller than the Raman scattering because we always have offset Raman scattering in such powder materials. And that is the spectrum for the flat without a laser crater. You can see that this is elastic scattering that was suppressed for 6 orders of magnitude. Still it's quite intense. And that is the Raman spectra. And as the hole is drilling, when you can laser, you can quite good Raman spectra and almost absent elastic scattering. Okay, these instruments were quite heavy in 70s and 80s and 90s, and there are a lot of teams who did it, including our institution. For example, our laboratory had used such big devices and helicopter or planes to make some lazy remote sensing, but it have no effect in real life at that time because it was very, very expensive to use such big aircrafts to make LiDAR measurements, and it always drops in 90s and zeros. And then, at the end of the zeros, unmanned aircraft vehicles became available at the market, and the price for their flight is much more smaller. So if you want to measure with these devices, you need to make a small LiDAR system. And everyone, including our teams, try to do that. So this is an example of the Raman LiDAR system we developed. It's quite heavy, it's about 2 kilograms, but at that time it was the most lightest, the most compact Raman LiDAR available in the scientific literature. It's based on diode pump laser that makes a laser pulse. It have a spectrometer group with gated detector, so it was rather sensitive, and we use this LiDAR for different purposes. For example, we use it for sensing water and water-related objects. Here is the example of ECA spectrum, and you can see different signals like elastic scattering as well as the Raman band. It's quite intense if we use it for water temperature measurement. Okay, why it was important to measure the water temperature remotely with a laser, with the lasers, with the LiDARs? That's because the satellite can't do it properly. They have too much error. And the microwave or scatterometers or laser scatterometers also makes very large mistake. Why? Because if you have a small wind above the sea surface, so the water molecules will evaporate more rapidly, and that means that the temperature of 30 thick microns layer will be lower. That is very precise and good measurements made by Solovyov and Lucas. So that's why scatterometers failed. But with Raman LiDAR, we measure somewhere here, about centimeters or half a meter or a few meters, so we can use it. The idea is basically shown here. So that is a part of Raman spectrum, that is intensity, that is the Raman shift. And you can see as the water heats, it's changed its envelope. For example, when we hit the water, this shoulder grows while this shoulder drops. So if we quantify the spectra at different temperatures, we can measure the water temperature remotely. And we did such systematic work. And first we use the traditional approach suggested in literature. And we got here, the idea is to separate into parts and takes iteration. We get the error about 0.61 Celsius degree, but then we decided another approach. It's a called centroid technique. We actually fit it with a single curve and find out the centroid of the curve and fit the centroid at the temperature and get much more better results. It's about 0.18 degrees. It's a good result for climate researchers because it's have good accuracy. Another application is of the LiDAR is to measure the thickness of ice. That can be very important because you need to find the best way for icebreaker to make them thinner ice, or you should be aware about the oil platform that installed in the northern Norway, not to damage by the thick ice. And we decided to use a Raman for that because traditional use just drilling, or it takes a lot of time and can be done automatically, but with a LiDAR you can do. The idea is based on that the Raman spectra of water and ice differed a lot. So that was our experiment. We have the same LiDAR I showed before, focus into the ice sample and move the sample or move the lens and measure the Raman spectrum. So we use two elastic scattering signal and Raman. If you use elastic scattering, you actually failed to, you easily detect the air to ice interface, but you fail to do it with ice to water because ice growing very slowly, so there are almost no defects, and it was not possible to do that. But if you if you add Raman spectroscopy, you can do. That's the same for elastic, and that is the centroid of transition between ice and liquid water, so it can be changed, and we measure it quite fastly. Okay, the good thing is, can we do it smaller? Because if you have a UAV, you need very small devices, and the answer actually, yes, we can. We have this in the future plan, but it's based on the system that was developed by Sergei Pershin. He will make a very nice talk in 30 minutes. He is a man who suggested to use eye-safe LiDAR, because before him, LiDAR always was something for military, not for the towns, not for the places where the human being can be. And he changed the situation early 90s and suggested idea, make a device, and even get a NASA project for this unique device. So just example what this device can do. They are completely different, and they can measure through some highly reflectant obstacles like trees. So you can see the tree, you can see the ground, and that was used to find out the hidden city of Maya in Mexico. Another example is self-driving car used nowadays, because with such device, eye-safe device, you can measure the distance to the obstacles. Here is an example at the distance of 100 meters at least. Even nowadays, such systems are used in cell phone like iPhone or iPads. And this is another example we used last year. We developed a fluorescence LiDAR for agriculture applications to sense, to install it on a drone and sense the dynamics of plants growing and help the agriculture to distinguish the poor region or good region of the field. Here is an example, it's quite small, about 30 grams. That's the device installed on a quadcopter, and that's device on the field with a laptop controlling it via Wi-Fi. So we can measure different spectra with diseased or healthy maize and make some maps that can indicate region with a poor soil or maybe some diseased plants. Okay, thank you. Thank you for attention. And I would like to acknowledge the funding agency for this support.
Okay, thank you for your presentation. We have some minutes for questions. And do you have some questions? No. Okay, thank you very much. It's very quite interesting, and I will continue some details in my presentation also. Okay, next presentation will be online. Are you ready?
Yes,
okay.
I'm ready.
Thank
do you
you.
hear me?
Let's start.
Okay, so do you see my slide?
Just a moment. We cannot see your presentation now. What's happened?
Okay,
Let's start again.
Okay, so now can you see my slides?
Okay, let's now it's small size only, but
okay.
Okay, Ben, we'll start. Fine.
Okay, so good day everyone. My name is Alexander Kuchmizhak. I represent two organizations, Institute of Automation and Control Processes and Far Eastern Federal University, both are located in Vladivostok. And actually, first of all, I want to thank the organizers for inviting me, but unfortunately this year I'm not able to come, but so you have to see my online presentation. And today I'm going to speak about application of laser ablation in liquid for synthesis of some hybrid metal semiconductor nanoparticles that we try to adopt for different applications. So this is an outline of my. I will start from some short summary, just reminding you the basic concept of the methods we apply to produce hybrid nanomaterials. It's a laser ablation in liquid, and also I try to show and explain why we want to synthesize hybrid nanomaterials. And then I will discuss our recent results related to general synthesis of two types of nanoparticles. First is the mixture of gold and titanium dioxide, and the second one is a mixture of common plasmonic metals like gold and silver with silicon. And in both cases, I will try to emphasize some structural and optical properties of these materials and also highlight some interesting application. Okay, so to start the introduction part, I want to mention that nanostructures that can resonantly interact with the optical radiation actually have been defined in the progress in such areas as metamaterials, optoelectronics, sensors, ultrasound optics, where this kind of resonant nanostructures are acting as a building block to build this kind of nice devices and materials. And first, of course, when we speak about optically resonant nanostructures, we can remember plasmonics, that is actually based on coherent oscillation of free electron plasma supported by noble metal nanostructures. And these actually nanostructures offers so this kind of oscillations of electron plasma can propagate along the metal dielectric interface, or can be localized within the isolated nanostructures. So it's called typically localized plasmon resonance, and this localized plasmon resonance offers you a very nice and strong localization of the incident electromagnetic fields near the surface of your nanoparticles or nanostructures. So you have very nice, very strong enhancement of the electromagnetic field, and you can localize it below diffraction limit. But basically, the noble metals, even the best of the noble metals, have non-negligible losses in the optical frequencies that somehow reduce the efficiency of the resonances. So probably 10 years ago, it was suggested a little bit different concept that suggests to use the audioelectric nanophotonics, mainly based on mirror resonances supported by generally nanostructures made of high refractive index dielectrics or semiconductors, that is usually silicon, germanium, titanium dioxide. And in this case, upon excitation of these mirror resonances, you can enhance the electromagnetic field not only on the surface of your nanoparticles, but also inside it. And as a consequence of this, you can expect to achieve some enhancement of nonlinear response from the nanostructure itself. And as long as we usually use some crystalline semiconductors to design this kind of nanostructures, these materials usually possess inherent Raman scattering that can be also enhanced because of this light localization inside the nanoparticles, like shown here. And as both areas evolve in parallel, scientists come to the conclusion that it will be a good idea to try to combine these both approaches and benefits of both approaches within some hybrid nanostructures, where benefits of both plasmonic and audioelectric nanophotonic concepts can be efficiently combined within some efficient design. But if we will check what sizes of the nanostructures required to achieve the resonant response in the visible spectral range, we will find that for plasmons, for plasmonic nanostructures, for nanoparticles, we typically need less than several tens of nanometers, but for mirror resonant nanostructures, we typically need at least 150 nanometers and even more. So resonance appears for dissimilar size of nanostructures. That poses a problem because it will be very hard to realize such kind of different dissimilar sizes and made of dissimilar materials with some common nanofabrication technologies like photo-ion electron beam lithography and so on. And I'm happy that in this conference I don't need to agitate for direct laser nanofabrication that is known to be cheap, flexible, and high performing. So here I put the video to show how this happens in the labs. You usually use here some laser source. Typically, it's a pulse laser source to fabricate something on the surface, to make some textures on the surface. And actually, when we try to think about the resolution of this method, we will find that for optical radiation, for lasers, we have this diffraction limit that actually defines the minimal focal spot size, that is lambda divided by numerical aperture of the focusing optics. And if this resolution will be even poorer if we will consider some thermal effects, because you typically couple your laser radiation. When you couple your laser radiation to the material, you have produce heat. So the heat affecting zone that is proportional to thermal conductivity of the material and thermalization time. So this heat affecting zone spreads, and if you somehow minimize this by using very short laser exposure, namely femtosecond laser pulses and materials with small thermal conductivity, you at least can achieve the resolution that is above the wavelengths. So it's several hundreds of nanometers for visible light. And of course, this is not nano. And of course, there are some tricks to achieve nano with lasers. And today we will be speaking about these tricks. It's one of the tricks is a very famous laser ablation liquid method, where we use the typically pulse laser radiation to shine to ablate the target that is placed below the liquid layer, and so the material removed by laser ablation condensates in the form of nanoparticles that directly ejected into the solution, producing the suspension of nanoparticles in a very simple way. And also, as this method resembles chemical synthesis, but in this case, if you don't want, you really don't need any chemistry. So this method can be considered as chemically pure. And of course, with this method, you can create very unique synthesis conditions, like very high temperatures, very fast quenching rates, and GPR pressures. So you can expect to see some kind of nanostructures with metastable phases, with very unusual composition, and so on. And finally, the method is rather flexible in terms of that you can actually ablate the bulk target, you can ablate the suspension of the produced nanoparticles, and that is more important in the context of today's study, that you can use the multi-material targets, or for example, suspension containing nanoparticles made of dissimilar materials for example, to achieve the nanomaterials with the shared material properties that we are searching and we want to achieve in our study. And to finalize the introduction part, in this slide I put the recent efforts of two groups to illustrate how the laser ablation liquid can be very nicely adopted to produce hybrid nanomaterials with shared properties. So this group is from Germany and Italy, and this group showed that the laser ablation liquid can be used to produce the magnetic plasmonic nanoparticles by mixing such kind of common plasmonic materials like silver and gold with common magnetic materials as cobalt and and iron. And this group showed a very nice application of these magnetic plasmonic nanoparticles for magnetically driven surface gun Raman scattering substrate, or these nanoparticles also show very nice self-degradation along with therapeutic effect. And okay, so as we try to first we try to mix the noble metals like gold with titanium dioxide with common semiconductor materials, and to do this we use the laser ablation in liquid, where we shine our nanosecond laser pulses to the suspension of commercial titanium dioxide nanopowder like P25 and some other fraction of those commercial catalysts. And plus we add some amount, it's typically at millimolar concentration, fluoroauric acid that serve as a source of metal upon thermal induced decomposition. And after several hours of irradiation of this suspension, we have managed to achieve this kind of hybrid nanostructures, where we have titanium dioxide core decorated with the gold nanoparticles. And of course we can tune the the average size of the core and the decoration degree by tuning the irradiation time, the initial size of the nanopowder, and of course the amount of chlorhydric acid in our solution. And to get a little bit more insight into the structure of the sensitized hybrid nanoparticles, we use the scanning electron microscopy tomography that is combined ACM imaging and focused ion beam milling to make multiple cuts that then were merged to create this 3D model of the structure. And this allows us to show that the gold is located not only on the surface of titanium dioxide, but also inside this. So this is shown by green, and the gold outside is shown by purple, just to distinguish between two types of gold in our system. And we use transmission electron microscopy combined with Raman spectroscopy to show that the structure of the titanium dioxide is completely amorphous. That is rather unusual because we started from titanium dioxide nanopowder that is crystalline. And resulting from these structures, the pristine titanium nanopowder that is white and highly reflecting, we have a very black material with the average absorptivity over 96% in the visible and near-infrared spectral range, so it's completely black and nicely absorbing. And we also found that upon amorphization, we have the reduction of the band gap of titanium dioxide from 3.2 to about 2.3. So we have the nice material with nice optical properties, and first we tried to use this material for sensing based on surface enhanced Raman scattering effect. Today it was the first talk by Bofes Minkiner, who already discussed this, the basics of the SERS substrate. And what we want to achieve is to enhance strong electromagnetic field on the gold nanocluster sitting on the surface of the titanium dioxide, and we achieve this by matching the pump wavelengths and diameter of the titanium dioxide to excite the ME mode in this titanium dioxide that pump additionally the gold nanoclusters on the surface of this nanoparticle. And we also found that upon amorphization, titanium dioxide completely lost its catalytic activity. Because we, as you remember, we started from nice catalyst material. It's pristine titanium dioxide nanoparticles. And this is good story for surface enhanced Raman scattering substrate, because when you absorb the molecules and during this kind of experiments, we can be sure that our nanostructures will not decompose the organic molecules through catalytic decomposition. And this is good, and with all this, by matching this mirror resonance size with the pump wavelengths, we achieve very strong and very nice self-performance of our nanoparticles. So these results were made only for single nanoparticles measurements, and the enhancement factor of surface enhanced Raman scattering enhancement was found to be up to 10 in order of 9 in detection of different molecular analytes like acridine orange, like that is molecular marker, and diphenhydramine, that is actually a dimidrol. And also, as long as we have very highly absorbing material, we can design a water purification and desalination system based on enhanced evaporation. And what typically can be done with this, people typically use two different approaches based on localized heating and volumetric heating. So for localized heating, you typically design some kind of porous membrane that you functionalize with your light absorbing nanomaterial. And for volumetric heating, you directly enter your nanoparticles into the liquid to enhance the evaporation rate. And so we have the nanomaterial with a very broadband absorption of the solar radiation, and you can see here the dynamics of the heating of the nanofluid composed where we add the gold titanium dioxide hybrid, and you can see here very nice and strong heating rate. And under one sun exposure, we achieved a 2.5 times faster evaporation rate comparing to pristine water. That is among the best results in the field, surely. So okay, and then we try to mix the noble metals with the most commonly used semiconductor as silicon. And to synthesize these nanoparticles, we use two-step approach. So first we ablate the bulk silicon target in isopropanol to create the suspension of pure silicon nanoparticles. Then we add chloruric acid at micromolar concentration and then irradiate the suspension of these nanoparticles to produce some hybrid nanostructures with very interesting morphology where gold penetrates deep inside the nanoparticles and occupies the space between this kind of silicon nanocrystallites that have the very irregular shape. And again, we use the SEM tomography to show that the core of these hybrid nanoparticles is mainly from gold, while the silicon nanoclusters are generally located at the interface. And of course, all this is also decorated with gold nanoclusters on the surface. And again, we have a very nice material for optical application, and we can think how to optimize the synthesis. And when thinking this, we can design some kind of fluidic device where we put our silicon wafer, for example, as a source of silicon nanoparticles, and we can inlet different analytes containing different salts or acids that is used as a source of metal in our system. As an output, we have nanoparticles with different shapes.
You have 2 minutes.
I'm sorry, I will go faster. We have nanoparticles with different size, morphology, composition, where we can tune this decoration degree and some other scene, and we also can so these nanoparticles can be used, for example, for surge detection, not for molecules, but for example, for detection of more complicated systems and processes. For example, we show the detection of the dimerization process of monomer molecules. It's paramine tillophenol to dimer azocaptobenzene. As you can see here, we have these additional lines appearing upon irradiation, and we can detect this reaction optically. And of course, we can we don't need to forget about the thermal band of the silicon that allow us a temperature feedback modality, because usually in Raman experiment along with the lines of our analytes, we have also this Raman band that shift when we hit the nanoparticles with the analyte, and this shift can be recalculated to local temperature. So this is important because molecular analytes have a very low decomposition temperature, and this will allow, this will give you a temperature feedback modality that is required for reliable measurements. And probably the last application I will discuss more briefly. So we have inherent Raman signal, and we also have the nonlinear luminescence pumped from hot electrons injected into the silicon nanoclusters. So we can create some random arrangement of the nanoparticles by just placing the drop containing suspension of these nanoparticles. And these nanoparticles create the very random distribution of characteristic Raman and hot electron-induced photoluminescence signal on the surface. And this kind of distributions can be used as an encryption case, because each deposition cycle is random, and a little bit size and morphology of the nanoparticles is also random. So nobody can repeat this kind of unique optical signal distribution on the surface. And with this, we can create some security labels that is impossible to...
Okay, your time is over. So
okay,
let's
so
conclusion.
we can create very nice security labels with very high encoding capacity. It's impossible to clone. And this is a conclusion of my talk. Today I try to convince you that laser ablation and liquid is a rather inexpensive tool for synthesis of hybrid metal semiconductor nanomaterials. It's fully scalable to create milligrams of nanomaterials with different morphology, shapes, composition, applicable for various applications. So kind of some of our recent papers. Russian Science Foundation is very thankful for support. Of course, thanks to our teams, guys, collaborators, and all of you for your kind attention.
Okay.
Okay, now we have a talk made by Sergey Pershin, who will present his last results, or maybe not last, but the most important results, with a new type of LiDAR.
Thank you.
Let me start with a presentation of my talk. I would like to mention about Nikolai Basov and Korokhin and Yuri Popov and the first proposals and design the first diode laser in beginning of 1960. You can see the успехи. And later, Jorel Salfyorov and Suris mentioned about and demonstrate the very high efficiency of the diode laser, about 80%. It's a very, very, very high efficiency, of course. And I would like to pay your attention that 30 years later, the Russian scientists have opened a new era of eye-safe environmental sensing by LiDAR, based on the Basov-Korokhin-Popov diode lasers, injection lasers, pulse lasers. And the main idea of this new era I will discuss later. So what does mean eye-safe is the main argument for our technology. This table shows us that the eye-safe, it's now we may estimate like energy density per square centimeters. In visible region, it's 0.5 microjoule per square centimeters. In the near infrared, when the diodes operate, it's around 1 microjoules per square centimeters. It's energy density that we may use without eyes protection. So when we develop of our LiDAR based on the new principle of remote sensing by using very, very small energy per pulse diode lasers, we can use it around the sensing of environment without eyes protection. This is the main idea, and we will try to discuss it now. So this eyes level, it's not spectral range, but it's energy density, it's main parameters. So this parameter was used for development of unmanned cars. It's based on our LiDAR principles. There's some steps mentioned about our papers, and you can find it. And one of them at new LiDAR era. It started in 1991. Next step is the first our LiDAR, which delivered to Mars by NASA missions. For the first time in history, Russian LiDAR was involved to the NASA mission to Mars, and it was delivered to Mars surface by 1999. And further, this LiDAR system was operated and opened the door to navigation, unmanned cars, and other platforms. And later, we used our LiDARs as a detector of Elbrus volcanic activity. We will discuss it later. Okay. It's some papers about our LiDARs, and I would like to show that our short materials was put in the Great Russian Encyclopedia. Okay, there's some examples of typical LiDAR system. It's large size and very, very, very massive. And our LiDARs, you can see here, very small. It can compare with a pen or some line. It's very, very small. You can find it in next presentation slides. Of principle, it's mentioned about Lyudnyov doctor's presentation. Some features of our LiDAR principle is gated quantum detector, it's single photon long diode, ultimately low laser pulse energy, digital circuits only without no analogs preamplifiers, and probability to signal detection much more less than unit per pulse. It's very, very interesting features. And high repetition rate also, we can use very high repetition pulsing. It's about 100 kilohertz. And adventures of our LiDARs is eye-safe environmental crowd sensing, high efficiency and stability, no interference with other instruments, no dead zone. No dead zone. It's very, very important for us because we can use large distance and very small distance to close to the docking, touching the targets without destroy it. Another features, we can measurement multi-layered obstacles, clouds, plumes, trees, canopy, and something like this. And the last one, it's no overload problems. We can use very high intensity of signals without destroy our single photon analog diode, such as detectors. Some examples of measurement of remote sensing from the clouds. You can see here these very interesting forms of response signals. You can see here tail. It's proportional of cloud density. Even we can estimate and make some tables for sort of different cloud system. You know, very tight clouds or very small clouds and something like this without but such instrumentation approach. We make classification of these clouds also. In other examples you can see here, we have demonstrated here the detection some layers, clouds, through the strong storms, snowstorms. You see, our signals was saturation because it's plate. And after this saturation, we can find signals from next layers over the 200 meters and another layers 600 meters. It's very interesting and very useful application of such LiDAR for meteorology. Another examples of our application, it's sensing the different layers near the Elbrus summits. Here's a trace, and this is a LiDAR. You can see fine there's a response such as in the lens. You can find two summit of Elbrus, and these are results. I would like to mention that we can detect clouds layers on the distance about 3 kilometers, 3,000 meters. You find here 2 layers because we used only 5 microjoules energy per pulse. Another application, I was invited in the United States, and we have measurement and detection forest fires to estimate the mass production of inside the forest fires. And next interesting fact that 1995 we have invited to have a competition for Mars Polar Lander missions. Different countries, you can see find United States, Europe, Canada, and another company make a proposal to different LiDAR system, but our LiDAR won this competition and was involved to this Mars mission. Okay, these letters demonstrate presentation of LiDAR system to this mission. Okay, now I will only show this our LiDAR before launching to the Mars. It was discussed, and the last part of my presentation, this tunnel inside the Baksan Neutrino Observatory. It's over the Elbrus chamber, and our LiDAR was still here. Now in this locate you can see fine, and there's some picture we tuning our LiDAR system. It's small size, and this picture demonstrates this LiDAR on the table, and this view of the, it's very small. It's monitor in our lab, we can find signals in Moscow in our institute from this black line over line. It's aerosol scattering, signals from LiDAR system. We can find very interesting results. Now we discussed it in publication. This black line demonstrates a strong fluctuation of LiDAR signals and scattering of aerosol inside this tunnel. These are another signals from water molecules, aerosol signals black, and rose it's from radon. In conclusions, I would like to mention again that the Russian scientists proposed and developed the new eye-safe LiDAR system based on diode lasers and spot technology as a detectors. Successful application for 30 years demonstrate that we have opened a new era in LiDAR sensing of environmental without eyes protection. There's a really new era. Thank you.
Thank you. Do you have any questions?
Now I would mention about this year is 100th anniversary of academician Basov Nikolai Gennadievich. It was in December of this year. Thank you.
Okay. Is there any questions? I have one. You have a lot of applications, but what you think about in the future, in 10 years? What application will be the most exciting, the most important for your device?
Thank you for your question. I believe it's very interesting application, and now we are planning to go to the underwater. It's interesting medium, underwater LiDAR sensing, in different application also for underwater platform, unmanned platform, and something like this. And of course, it's unmanned cars in something different application, some ship, and another application inside this environmental medium. Okay.
So,
thank you.
Is there any questions? No? Thank you. And now we have the next speaker. It should be Ryzlakovsky. Okay. You have a talk. Thank you.
Good afternoon. My talk is named Fiber Optical 3D Current Sensor with Enhanced Signal-to-Noise Ratio. Our group is doing our research about current sensing by applying the optical methods. Our current sensor is based on the magneto-optical Faraday effect. It is the effect that if we have a linearly polarized light wave propagating in the medium in the presence of external magnetic field, the direction of polarization is the direction of polarization rotates, and the angle of its rotation is proportional to the magnetic field. So the simplest way to measure the electric current using this method is to form a linearly polarized light wave and inject into the sensing fiber wound around the current around the conductor with current. The most commonly used type of optical fiber as a sensing fiber is a so-called span fiber. It's a birefringent fiber which birefringent axis rotating along the fiber. Such a fiber have a property suitable for using the Faraday effect, that it maintains almost circular polarization of the light wave. If we use the Faraday effect for current sensing, the Faraday effect is the most usable for measuring large currents, but in the same time it have a very little time of relaxation, so about of order of the 10 in minus 9 seconds. So this method is maybe suitable for measuring low current pulses. And here in this work we design the special scheme, optical scheme of the current sensor to measure such small pulses. It can be the application of this maybe, for example, measuring currents in particle accelerators, or maybe something about this. But if we want to measure small currents, we must take into account three things. The first of is the noise, where we must care about the enhancing the signal to noise ratio. The second is time resolution and the sensibility. This can be enhanced if we reduce the winding radius of the fiber, so we can make more fiber turns about the around the conductor and increase the sensibility. Here we present the upgraded optical scheme of the fiber optical current sensor with optimized to measure little to measure small current pulses. The first we we inject here the subsystem to compensate so-called excess noise. And the second, we use modified sensing coil depicted here. What this upgrade, what the effect of this upgrade? First, about the noise. Traditionally, in such optical devices, the light sources are superluminescent light sources which have a broad spectrum. And if we use light source with broad spectrum, there is excess noise in the output of the sensor. This excess noise emerges due to the beating of light components. Here we have two, for example, spectral components, and if we add them, we will get the amplitude beating. So beating of every pair of spectral components along the spectrum gives the excess noise in the output of the sensor. But this noise can be subtracted if we take some part of the optical signal before before its interference and inject it into the reference photo detector. Here you can see the noise without the compensating of the excess noise, and the green line shows the compensated signal. So using this subsystem, we got the noise suppression of about 6 times. Here you can see example of detecting the current pulse of about current was 20 to 12 amperes and pulse duration 300 nanoseconds. Here 2 curves without excess noise suppression and with suppression of excess noise. So about the sensing coil, if we use a large radius of winding of sensing coil, there is only a few fiber turns we can wander around the conductor. So to increase the sensibility, one way is to reduce the radius of winding. So use such small sensing coils. In the example here, we use 2 different winding radius over 100 millimeters and 5 millimeters. So fiber turns correspondingly is 15 and 300. But if we reduce the winding radius, there is emerging bending birefringence in the fiber, which disturbs the polarization of the light. This leads to the disturbance of the optical spectrum of the registered light. So due to this distortion, the effectiveness of excess noise suppression decreases, and instead of 6, for a factor of 6 times, as I showed earlier, here we have only 2 times. We elaborated the theoretical model of propagation of polarized light in the spun fiber and got the formulas for expressions for polarization modes in the strongly bent spun fiber. This theory helped us to reveal the mechanism of decreasing of effectiveness, noise suppression effectiveness, and the way to deal with this is to work around this and increase the noise suppression factor is to use such a special winding with smooth changing of the winding radius. The theory shows that then the polarization modes...
I'm sorry, 1 minute.
Okay. The polarization modes converts also smoothing and recovers the circular polarization at the end of the optical scheme. And the optical spectrum also is recovered. So applying such a special winding, we have a small radius winding, so we have a high sensitivity of the sensing coil, and we recover the high factor of excess noise suppression, about 6 times. So conclusions. We designed an upgraded scheme of current fiber optical current sensor based on the Faraday effect, adopted to optimized to measure short and small current pulses. We revealed the mechanism of reducing the excess noise suppression when we use the sensing coil with small radius, and propose the method of sensing coil winding, which recovers the high factor of suppression of excess noise. Thank you.
Okay, thank you. Is there any questions? Okay, I have one question about, can you compare your device? Because I like the device that you can use optics to measure the magnetic field. So in some application it will be extremely important because you do not have any impact on magnetic field via your measurements. Can you compare your device with those have commercially available at the market? One question. The second one, what are applications except accelerator?
The most common application, as I said, is to measure large currents. It is mostly designed for electrowinding industry or power plants, and the advantages of optical measurement method is that we use all the electric parts. We don't have to use any metal parts.
It's safe.
It's safe. It's safe. No, we don't know to touch, and as you said, the current, the conductor, and if we speak about applications where the high voltage applications, these devices are very small and compact in comparison to traditional transformers.
Okay, thank you. Any more questions? Okay, thank you, the speaker. And let's go to the last but not least talk by Morshnev. Please come. He will tell us about utilization of interference method for studying superluminescent source.
Интерференционный метод для отбора однородных линий в спектре суперлюминесцентного источника. Ну, метод заключается в том, что два волновых пакета, изучается интерференция двух волновых пакетов, у которых может быть изменена время когерентности, и они могут быть сдвинуты на фиксированное время друг по отношению к другу. Значит, это значит, установка для изучения суперлюминесцентного диода эрбиева. Так. Вот. Значит, это вот эрбиевый источник. Простите, я сказал диод, да? Значит, волоконно-оптический источник эрбия, излучение которого поляризуется в волоконном поляризаторе и через 45-градусную сварку поступает на линию задержки. Это обычное волокно с большим двулучепреломлением. Вот. Здесь происходит из-за 45-градусной сварки происходит разделение, значит, на два пакета волновых. Значит, один из них, да, эти пакеты равны по своей длительности, но отличаются, значит, своей поляризацией. Вот. Ну, понятно, почему это происходит. Значит, двулучепреломление предполагает разные скорости распространения волн с ортогональными поляризациями. Далее, здесь тоже должна быть 45-градусная сварку, но мы, значит, поставили здесь прибор, который можно точно осуществлять повороты. Вот, и этот сварочный аппарат. Вот, и здесь мы, значит, подбирали, значит, этим поворотом подбирали минимальную видность, в смысле максимальную видность картинки, которая получается, значит, в результате всех преобразований. Значит, для чего вот эта 45-градусная сварка? Для того, чтобы можно было, ну, после прохождения анализатора, ну, поляризующего элемента, вот, наблюдать интерференционную картину на спектроанализаторе с разверткой по длине волны. Значит, спектроанализатор играет тут несколько ролей. Значит, ну, первая развертка по сканированию по длинам волн, и второе это то, что у этого спектроанализатора можно изменять разрешение, то есть формировать те пакеты, которые нам нужны по длительности. Значит, у него есть декадный переключатель у спектроанализатора, есть декадный переключатель от 0,02 нанометра до 2 нанометров, то есть перекрывается диапазон разрешений на 2 порядка, и тем самым, значит, это позволяет нам, значит, изменять длительность, когерентное время когерентности. Когерентное время — это английский значит, время директности этих самых цугов или волновых пакетов. Значит, вот это те формулы, которые... Вот это два этих самых волновых пакета. Вот это определяется, значит, задержкой фазовой, то есть длиной биений этого самого волокна с сильным лучепреломлением, вот, и его длительностью. То есть мы можем вот этот вот период вообще менять, изменяя длину волокна задержки. Вот это, значит, вот длительность этого импульса определяется разрешением спектроанализатора. Вот это типичный случай вот, интерференционной картины. Значит, спектр источника представляет собой такую двугорбую кривую с шириной по спектру, значит, около 20 нанометров. Вот. Значит, здесь следует обратить внимание на минимальные значения и максимальные значения интенсивности. И связано это с тем, что вот этот вот минимум интенсивности зависит, от этого минимума интенсивности зависит видность интерференционной картины. И вот, значит, оказывается, что оказывается, что минимальные значения, значит, они очень сильно зависят от видности, и поэтому позволяют нам определять ее достаточно точно вблизи, когда видность порядка, значит, единиц. То есть, вот, значит, видность, вот, в случае, если у нас, имеется только вот этот вот механизм, то есть сдвиг двух цугов один относительно другого, то, значит, естественно, формула очень простая. Вот. Значит, и если мы будем изменять разрешение, то есть будем его, скажем, ухудшать, то есть возьмем с 200 и будем, значит, постепенно ухудшать это самое разрешение этого приемника, вот, то в конце концов наступит такой момент, когда вот начнет ограничиваться длительность этих самых цугов, начнет ограничиваться не вот этой формулой, а начнет ограничиваться собственной шириной этого самого источника. Ну вот, значит, что получается? Когда мы ухудшаем разрешение, то вначале, значит, у нас по спектру нет все видности одинаковые и близкие к единице. Вот. Это у нас 2 десятых. А вот это вот 5 десятых. Значит, что это означает? Это означает, что здесь вот это вот разрешение спектроанализатора стало больше, чем ширина линии, однородной линии у суперлюба. Вот. Поэтому, значит, началась зависимость от положения по спектру. Вот. Ну, значит, если мы посмотрим дальнейшее, да, и кроме того, сильно изменилась, ухудшилась видность интерференционной картины. Это что означает? Это означает, что у нас разрешение стало, значит, дельта лямбда стало больше, чем разрешение, обусловленное источником, самим источником. Вот. И, то есть, начиная с 0,5 нанометров у нас будет зависимость, значит, все, так сказать, хуже и хуже, видимость будет падать, и сильнее она будет зависеть от спектра.
У вас минутка осталась.
Ну,
1 минута.
Все, значит, то есть мы таким образом получили зависимость от этого самого спектра и получили возможность определить однородные, значит, ширину однородной линии. Спасибо за внимание.
Спасибо. Будут ли вопросы? А у меня такой вопрос. Вот у вас на 1,5 микрона все сделано, а для других оптических диапазонов?
Ну, это обусловлено...
Нет, можно ли это перенести в другие диапазоны?
Ну, конечно,
2 микрона,
да, нет, конечно,
полмикрона?
Можно. Нет, можно перенести. Речь идет только о том, что, скажем, вот лазер, у него однородная линия сама по себе, и поэтому у нее такой проблемы нет. Вот. А это тоже лазер, вообще-то говоря, однопроходной. Значит, это вот та самая...
Ну, суперлюминесценция.
Да, суперлюминезиум, да. Вот, но дело в том, что время жизни порядка 10 минут с 11 секунды, и, следовательно, длина этого самого цуга в вакууме составляет порядка 4 миллиметров. Значит, разница между лазером и этим просто в длинах. У лазеров километр, а здесь 4 миллиметра.
А каким образом вы такие короткие получаете импульсы?
10 секунд.
Это не импульсы, это не импульсы.
А, это время жизни...
Это вот идут цуги, у них длина, время когерентности составляет вот ту величину, которую я сказал.
Время когерентности тогда, когда он интерферирует, да?
Да, вот дальше, да, это влияет на интерференцию. Да, отрезок.
Спасибо. У нас, да, объявление у нас в синем зале, сейчас переходим, там будет закрытие.